In the previous video, we looked at the end behavior of a function, and a lot of that can come from standard form. So standard form, as a reminder, was just expanded all the way out where you have x to an n power, that highest power, there's some coefficient in front. And so here's an example, 3x to the fifth, 6x to the fourth, minus 2x cubed, plus x squared, plus 7x minus 6. In this, the highest exponent is 5, so it's x to the fifth. This makes it a degree 5 with a leading coefficient of 3. All of the coefficients are the values in front of the variables. That last term is our constant term like we talked about with quadratics. And from these, with the degree, we can tell how many roots that polynomial will have. It also helps tell me what the end behavior is going to look like. Now, roots are another way to talk about zeros. Roots and zeros are synonymous, or synonyms, but they are the solutions to when the function's equal to 0. So it's similar to an x-intercept, except sometimes these may be real or imaginary, and only the real roots show up as x-intercepts. So we can't really say that they are all x-intercepts, because if they aren't real, if they're an imaginary root, an imaginary zero, that is not technically an x-intercept. So if that polynomial is in factored form, it's really helpful. Factored form is useful because you can easily find the roots or the zeros of that function. And we do that by using the zero product property, something that we've already talked about with quadratics. But let's put a little reminder here. If we're talking about the zero product property, and I have two things being multiplied, so that's a product and it's equal to 0. The only conclusion we can make is that one of these factors must be 0. So if I put more than two factors, and this whole product is equal to 0, as long as one of them is 0, the whole product is 0. I could have 7 times 2 times 0 times 4, and I know that product is going to still be 0 because one of them is 0. So in the zero product property, you will set every single factor equal to 0 and then solve. So I'm giving you a few of these functions already in factored form. In a later video, we'll talk about how do I actually put something in factored form. So we're going to write these out. We've got a factored polynomial of x minus 3 times x plus 4 times 2x minus 1. If we set this function equal to 0, and that's how we find the roots, then I would set the factors equal to 0, so x minus 3 equals 0, x plus 4 equals 0, and 2x minus 1 equals 0. Once we have those factors, then we can set them equal to 0 and solve to get the roots. That means I have a root at 3, another one at -4. We got to do a little bit more solving for the last one, but it's at 1/2. So the roots we can classify are 3, -4, and 1/2. If I look at the second one, there's a -3 x plus 8 times x minus 4 squared times 5x minus 3. Setting this equal to 0, we've got 0 equals -3 times x plus 8 times x minus 4 squared times 5x minus 3. That -3 does not have a variable with it. So there's no way that that can make this part of the product, or sorry, part of the product that makes it equal to 0. If I had -3 times 7 times 0 equals 0, the -3 didn't make this product equal to 0. The 0 did. negative 3 times a times b equals 0. Negative 3 is negative 3. It can't make the product equal to 0. But a can make it equal to 0, and b can make it equal to 0, just not the negative 3. So we've got this negative 3 that we're going to kind of ignore and just set the factors x plus 8 equal to 0. This x minus 4 is happening twice. So you could write x minus 4 equals 0 and another one, x minus 4 equals 0. And the last one's 5x minus 3 equals 0. We're going to solve and get negative 8. If I solve x minus 4 equals 0, I get positive 4, but there's two of them, so really there's two of these positive 4s. And then we solve the last one and get 3/5. What we're seeing now is that 4 came up twice, which is called a multiplicity. So if I write out these roots, I'm going to say x equals negative 8, x equals 4, multiplicity of 2. And then x equals 3/5. These only came up once, so we could list them as multiplicity 1. We just don't really have to. For this third one, it's still in factored form. I'm going to set it equal to 0. So 0 equals x squared times 4x minus 1 times x plus 5 cubed. If I set each one equal to 0, this x squared I can set equal to 0, but that could also be a single x times another single x, so x times x equals 0, where you're still going to get x equals 0. There just happen to be two of them, so what's multiplicity 2? If I set this 4x minus 1 equals 0, we would solve it and get x equals 1/4. There's only one of those, so it's a multiplicity of 1. And then the x plus 5 equals 0 gives me x equals negative 5. There are 3 of these because it's to the third power. So those multiplicities will impact the graph of that polynomial. We'll talk about that in the next video. So I would write this out as x equals 0, multiplicity 2. You can abbreviate multiplicity if you want. X equals 1/4, and x equals negative 5 multiplicity of 3. One more here, we've got f of x equals 1/5 x squared plus 4 and x squared minus 7. Setting this function equal to 0, we see that that 1/5 is still just some kind of constant multiplier out here. It doesn't have a variable with it, so it's scaling this function. It's actually shrinking the function, but it is not creating some opportunity to be 0. Just the other two factors are, because those have variables. So I'm going to set this x squared plus 4 equals 0, and then x squared minus 7 equals 0. If we solve these, x squared plus 4 equals 0 moves the 4 over, so it's x squared equals negative 4. We would square root both sides, but remember when we take the square root of both sides, we have to think about the two options, that's positive or negative square root of negative 4. Automatically I see a negative there. That means I have an imaginary number. Now the square root of 4 is nice. If this had just been positive 4, we know that'd be 2. But since it's negative 4 inside, this is 2i for the imaginary part. X squared minus 7 equals 0 makes this x squared equal 7, and taking the square root of both sides makes plus or minus. We get plus or minus square root of 7. The square root of 7 does not simplify. Now if it did, we would want to write that simplified, but we get these roots. And it looks like there may only be 2, but remember there are plus or minus, so that's actually 2 and 2, so 4 different roots. if we had multiplied this out, gotten it into standard form, we'd see the highest exponent is 4. It is a degree 4 polynomial. So we could write this out where we have one root at 2i and another root at negative 2i. We have a root at square root of 7 and another at negative square root of 7. Those are the 4 roots. The degree of the polynomial helps me know how many roots there are. If we want to work the other way, if I know how many roots there are, then that also tells me this is a degree 4 polynomial.